with the open system, we're going to have a change of substances. We have the air, we have the products of combustion, and so now our open gas turbine system. So I'll have a compressor, combustion chamber, fuel goes in here into a turbine. Part of the work of the turbine goes back here, and I'm going to have the network go out here. And we have 1, 2, 3. So that's when we have the air goes through, it's compressed and all that sort of stuff. And then on the TS diagram, goes 1, isentropic compression ideally, state 2, combustion from 2 to 3, which is the heat in, 3 to 4, the expansion through the turbine, and the pressures at 1 and 4 are the same. And T3, so T3 in this case, I have my combustion chamber, and it's determined by the adiabatic flame temperature, so the chapter 12 information we had about adiabatic flame. So T3 adiabatic flame temperature. And what happens with a combustion chamber, so if I take the combustion chamber, like this, there's a lot of air blowing in here, so I'm going to have fuel come in. So the fuel goes in the center, and then this is I have the air coming in at state 2, right? So at state 2, the air is coming into the combustion chamber. It's going to mix with the fuel, but I don't want all the air because we're dealing with maybe 300% theoretical air, so there's a lot of air. So what we do is we have some of the air bypasses. So in the combustion chamber itself, sometimes there are holes, there are fins, so what happens is I have bypass air, and I have air going in here. And so my combustion process occurs in here, and then because this is metal, I have air coming in across the metal, keeping the metal cooler, so I don't have metal fatigue, and then it comes out here at state 3. So then I have T3. And so now let's look at example 14.4. And again, read this because I'm going to speed up the process. So in this case, we have that the network produced by this is 600 kW. We have that R sub P is equal to 10. T1 is 300 K. P1 is 100 kPa. RFA is equal to 0.015. We have C12H26, so H sub RP is equal to 44,102. We have for the products, we have that K is equal to 1.33. C sub P of the products is equal to 1.15. And R is equal to 0.285. And now what we're going to do is go through the cycle on the cycle analysis and figure that out. And so we have this given information for our gas turbine unit. So I have, this is my diagram, I see what's going on, and now we're going to go through the open system analysis and do this. I can't keep all my drawings. but you have them to refer to. So now, the work of the compressor is equal to H2 minus H1. And notice that we're going to do everything per unit mass, and then I'll correct for the mass flow rate at the end. So in these problems, we do work per unit mass, and then correct at the end. Is equal to C sub P, T2 minus T1. T2 is equal to 300 times 10 to the K minus 1 over K. And K for air. So for air, which is in the compressor, we have this, so we get that T2 is equal to 579.6 degrees K. WC is equal to C sub P 1.0047 times 579.6 minus 300. We have WC is equal to 280.9 kilojoules per kilogram. Let's do a first law on the combustion chamber. We don't know. We're told RFA, but I don't know what T3 is. So we have to do a first law on the combustion chamber to determine T3. And this will give us T3. So En equals E out. So we have H2 plus RFA, H sub RP. The energy of the air, the energy of the fuel, and the energy of the products leaving, 1 plus RFA times H3. So we have C sub P T2 plus RFA H sub RP is 1 plus RFA C sub P of the products times T3. If I substitute in, I have 1.0047 times T2, which is 579.6, plus 0.015 times 44,102 is equal to 1.015 times C sub P 1.15 times T3. So I can solve for T3, and T3 is equal to 1,065.6 degrees K. And I know P3, so I know P3 is the same as P2. Is equal to 1,000 kPa. And then I can find T3 with the reversible adiabatic isentropic relation, or T4 rather. T4 is equal to T3 times 1 over R sub P to the K minus 1 over K. And K is equal to 1.33. So I'm using those values for K. I'll come up with that T4 is equal to 601.9 degrees K. So you can substitute in and do the numbers. And so now I can find the work of the turbine is 1 plus RFA times H3 minus H4 is equal to 1.015 times C sub P, 1.15 is C sub P of the products, times T3 minus T4, 1065.6 minus 601.9. So I get that WT is equal to 541.2 kilojoules per kilogram. So now I have the turbine work and the compressor work. I can find the net work. And so that's equal to 260.3 And I can find the air flow rate because I know that this thing, this W dot net is 600 kW. So I know W dot net is this, so now I can find the mass flow rate. So M dot A W net is W dot net. So M dot A times 260.3 is equal to 600, or M dot A is equal to 2.30 2.305 kilograms per second. Sometimes my writing and talking interferes with my tongue. And so then we have that the thermal efficiency is equal to W net over RFA H sub RP. So we have this is 260.3 divided by 0.015 times 44,102 is equal to 0.393. So we have 39.3%. And we have the volume flow rate. We have that the volume flow rate, V1 dot, is M dot R T1 over P1 is equal to 2.305 times 0.287 times 300 over 100. I have that B dot 1 is 1.99 cubic meters per second. So what we have is a huge volume flow rate. So the way the Brayton cycle is able to produce so much power is that this is 2 cubic meters. Think about how big a cubic meter is. There are 2 of them per second flowing through this thing. That's how they produce the power. They have a huge mass flow rate, volume flow rate, and hence they're able to produce a lot of power in a short amount of space. And now what I want to do is continue on the discussion of open gas turbines, and we'll look at turbine efficiencies. So I want to take this, we took an example, and now what I want to do is look at an actual gas turbine with actual numbers that we have associated with its performance, and we'll calculate the efficiencies, and then we'll have an extension here to begin to look at the high temperature leaving. So part of what happens when you go back and look, this T4 is fairly high, so it's a high temperature, and what are we going to do with that? And the analysis that we'll be looking at will further highlight that instance, and then we'll get to the next topic, which is regeneration after this. So now we're going to look at problem 1415. So this is a problem at the end of the chapter. So it's a homework problem you don't have to do because I'm doing it here. But again, look at it so that you see what's going on. So anyway, I'm going to just draw the compressor. I'll provide the information that's here. So at state 1, we have 4.72 cubic meters per second, 27 degrees C, 100 kPa. So that's the standard temperature and pressure inlet conditions. It's coming out, going into the combustion chamber, it's coming out at 517 kPa and 220 degrees C. Call this 2 prime. Whenever you're given a problem and they tell you the conditions, Do not assume that's the isentropic conditions. That's the actual conditions. You're going to have to find the isentropic ones. It goes into a combustion chamber, and I'm told here that RFA is 0.015. Seems to be a popular RFA these days. Then it goes out into here in state 3 and goes into the turbine. Going to have to work there. We're going to have W.net coming out of here and down to 4 prime. And 4 prime is 105 kPa and 454 degrees C. So notice that the exit pressure is a little higher because often on industrial units you have an exhaust stack or exhaust pipe you have to go through, and it has to be a little bit higher than atmospheric pressure for that to happen. So we have this information available to us, and what we're going to do is we're going to find the mass flow rate. So we have the volume flow rate here. Let's find the mass flow rate.